Okay, we're back. All right, we are going to solve a Gauss's law problem. So we have the mass of the Earth distributed a little bit differently in that the inner 20% radius is hollow. And so we're kind of picking this problem up midway, where we're going to try and solve for what the gravitational field is at some radius here that's in between the point where it's hollow and in between the outer edge of the Earth. Okay, so Gauss's law says the closed integral, right, of g dot dA is going to be negative 4 pi g times the enclosed mass. So first we have to figure out a general expression for the enclosed mass. Okay, so we want to do something like our enclosed mass is a density, which we need to calculate, times the enclosed volume. Okay, so first our density is going to be mass over volume. And the problem says that the mass is still the mass of the Earth. Okay, so that part's easy. But the volume, again, this is the volume that the whole mass is spread out over, right? So it's this whole outside area, or volume. So our volume that's holding the mass is going to be the whole volume of the Earth minus the volume of the hole. So our volume of the Earth is 4/3 pi times the radius of the Earth cubed. And then we'll subtract the volume of the hole, which is 4/3 pi, and then we have 0.2 radius of the Earth cubed. So our density is then the mass of the Earth divided by 4/3 pi. I'll just factor that out, and I have the radius of the Earth cubed minus 0.2 radius of the Earth cubed. So I could even factor out a radius of the Earth cubed. So it's mass of the Earth, and then 4/3 pi radius of the Earth cubed, and I get 1 minus 0.2 cubed. Okay, so we could figure out a number, but we'll come back to that later. Okay, and then okay, so if I go back now to Gauss's law, right? So I'm always going to pick a surface, a closed surface that reflects the symmetry of the problem, right? So I'm just going to pick a sphere of radius little r here. And I'm picking it so that it reflects, or I pick a surface where I think the gravitational acceleration is constant along that whole surface. So I can just pull that out of my integral. So g comes out, and then I still have my integral of dA. And then 4 pi m enclosed. Oh, and we forgot this, didn't we?
And we need G too, right?
Oh, yes, thank you. Forgot G.
We forgot that.
Uh-oh. Okay, and then, so our enclosed volume is going to be similar to this, right? Like, it's just going to be the enclosed volume that actually contains mass. So it's going to be 4/3 pi r cubed, where r is the radius we're measuring. It's just a radius that varies between 0.2 and the edge of the Earth. And then we're going to subtract the volume of the hole, which again is 4/3 pi 0.2 re cubed. So we can use this and this to get our enclosed mass. Right, just the product of those. Okay.
Wait, oh.
So the enclosed mass, right, is going to be our density times the enclosed volume.
Okay.
So you subtracting this part was not clicking?
No, the fact that R, how that was different than where you calculated the density volume. Like I was having that cancel out every time.
Oh, I got you. Yes. Right. So this is the density of the whole Earth, right?
Yeah. I understand that now.
Yeah. Okay. Okay, so then we're going to integrate, we're going to integrate dA around the whole sphere, so, right, so we get G, and then this ends up just being the surface area of the sphere, 4 pi r squared. And then we get minus 4 pi G over here. And we're going to copy down our expression for the density. So that's going to be m Earth over 4/3 pi radius of the Earth cubed minus 0.2 times the radius of the Earth cubed. And then we'll bring down our expression for the volume. 4/3 pi r cubed minus 4/3 pi 0.2 radius of the Earth cubed. Okay, so we have 4 pi's on both sides, so those can go away. We have a 4/3 pi in here that can cancel out with those as well. And so I'm going to divide by, well, we'll wait, we'll do one more. So G r squared is negative G times the mass of the Earth okay, and on the top I have r cubed minus 0.2 radius of the Earth cubed, and on the bottom I'm left with radius of the Earth cubed minus 0.2 radius of the Earth cubed. So this part's just a constant. I can kind of move that to the side. So now I'm going to divide through by r squared. So I get G is negative G mass of the Earth radius of the Earth cubed, 1 minus 0.2 cubed. That's this term coming down. And then I get 1 over r squared, r cubed minus 0.2 cubed radius of the Earth cubed. Okay, so if I factor that in, okay, so inside my parentheses I get r cubed minus, or divided by r squared, so that's just an r. And then I get 0.2 cubed radius of the Earth cubed over r squared. And we'll pause it right there.